Hey, welcome back. We're going to continue with another example of Jacobian substitution. So we're asked to find this volume, but don't evaluate it, okay? We're asked to find this volume of this equation right here, given the following constraints. Now notice we have two hyperbolas and two horizontal lines, and we're given the following transformations. How they come up with these transformations, just remember, they're just picking things for x and y that'll make these look very nice. Maybe horizontal lines and some vertical lines. So the first thing we got to do is, well, I want to take a look at what this looks like. First of all, my original base R is going to be these two hyperbolas, and y equals 2, y equals 6. So we're looking at this region right here. Now obviously that's a pretty nasty little region that we want, so this is not going to work out well for us. So let's go ahead and get the new base, because it's all about that base, no trouble. So the first one they tell me is x, y equals 1. So when I substitute in, I'm going to get this v over 6u times y, which is 2u equal to 1. The u's here cancel, and we're left with v is 3. Oh, that's nice already. So this went from a hyperbola to a horizontal line. Remember my new one, v is like my y. So the next one, if I have x, y equals 3, well now we got this v over 6u times 2u equals 3. Same thing, we get v equals 9. Ooh, already nicer. Alright, now next we got y is 2. Well, that's not too bad to do. Well, y is this 2u equals 2. U is just 1. Where y is 6, we can say 2u is 6. U is 3. Sounds bad to say that. U is 3. Alright, but let's just look how much nicer this is, though. Ready? Here's my new base, because it's all about that base. If I let my u's be my x's and v's be my y's, my v's go from 3 to 9, and my u's go from 1 to 3. We're looking at this rectangle. So rather than have all this curvy-licious function right here, we now are left with a rectangle, and that's much nicer to work with. I can get my new limits now. My change in u, or my change in v, I should say, I can go vertical, goes from 3 to 9. And my change in u's are going to go, this is going to move right and left from 1 to 3. Now next, that's the ugliest looking 3 I've ever seen. There we go. Next, now we have to change the inside. Remember, this is a substitution. Like last year when we did substitution, like if I did substitution last year, like if I had like the integral sine of 2x dx from 0 to pi, whatever, I have to change everything that has an x in it. Everything. So we just changed the domains. Remember, now we have to change the function in terms of not just u here. We have to change the 2x over here in terms of u. Up here, same idea, we have to change this xy cubed. So we have to change this xy cubed right here. And in terms of u and v, and they tell us what those are. Xy cubed. They tell us what those are. Down here, last year, we would say, we're going to let u equal 2x. We found it for ourselves. Up here, they're going to tell us for the most part, for now. So if I solve this, this becomes v over 6u times 2u cubed. And this becomes, let's see here, 8 v u cubed over 6u. And that reduces to what? 4/3 v u squared. So there's my new inside, my new function right there on the inside. So we just changed our function right there. And now we have to get dA. Remember, dA is our Jacobian, the absolute value of our Jacobian, dv du. So now we have to get our Jacobian. To get the Jacobian, mate, that's our determinant. We're going to take the derivative of x with respect to u. Oh, that's nasty. But v is a constant, u's on bottom. So this becomes negative v over 6 u squared. The derivative of x with respect to v, that's nice because this is just a constant. We get 1 over 6 u. Take the derivative of y with respect to u is 2. The derivative of y with respect to v is 0. Man, I thought this was going to be a problem, but it's not. It's just 0. So we get 0 minus 2 times 1 over 6 u, which becomes 1 over 3 u. And there's our Jacobian. Jacobian. And now I'm ready to write my new integral. My volume is going to equal, okay, didn't leave myself too much room unfortunately, it's going to be my function 4/3 v u squared times my Jacobian, which is this, this should have been a negative, but it doesn't matter, it's going to become positive anyways, but I want to be careful. And then dv du. There it all is. There's my entire new integral. And I can simplify this by factoring out the 1/3 here, and I'm going to get 4/9 v, be careful, this just becomes u, dv du. And remember, my change in v's go from 3 to 9, and my u's go from 1 to 3. And this is not that bad to solve, because one, I'm getting rid of the number of integrals I would have to use. Notice, I went from having multiple integrals, like if I tried this one, I mean it could be like this, this. I mean this could have like 4 integrals, but here we only have 1 integral to solve. Very nice. All right, our last example. Using a Jacobian, we want to show the conversion to polar is dA equals r dr d theta. So we're actually going to prove using Jacobian substitution how we get the polar area right here. So we know from polar, from earlier, that if my dA is dy dx, if I convert that to polars, we get r dr d theta. So that's our rule for polars. We want to prove this. Now, the only difference though is in polars, we're going to use r and theta, not u and v. So let's see here. Ready? Let's just see. Remember, I'm only converting, give me a second here. I'm only converting this part. So I need, what's my rule say? I need my Jacobian, and I need my little base, which is in this case dv du. So what we're going to convert is this dA part right here. Well, we know that this dA hat, right, our dA hat equals our Jacobian, this is our rule, times dv du. So we just need our Jacobian right here. So let's go ahead and get that. Well, we're using polars, so let's go ahead and get r, x and y. X is r cosine theta. Y equals r sine theta. So let's go ahead and get our Jacobian. Ready? Let's see here. The derivative of x with respect to r is just going to be cosine theta. The derivative of x with respect to theta would be, remember this is, so let's see here. So kind of give an idea what's really going on here. We want the derivative of x with respect to r, which is cosine theta, the derivative of x with respect to theta, which is negative r sine theta. Now we want the derivative of y with respect to r, which is sine theta, and the derivative of y with respect to theta, which is r cosine theta. And if we do this, if we simplify this, we're going to get r cosine squared theta plus, I'm going to go plus, it's a minus, but it's a negative, r sine squared theta, which is just equal to r. So there's my Jacobian. So there, what is dA going to equal to? Well, my Jacobian, dv du, which is, well, my Jacobian we just said is r dv du. And there, and of course we're not using v's and u's. Remember, we're using what? That's right, r's and theta. So we can just prove that our polar substitution is also a Jacobian substitution. All right, hope you enjoyed the video. I'll see you all later. Bye-bye.